All right. So today we're talking about the Euler's characteristic in the utility problem. So this is week 13, I think. So when we're talking about Euler's characteristic, we talked about that in terms of the graph. And way back at the beginning of the semester, we talked about graph theory. So let's just recall that graphs are collections of edges and vertices. And where an edge, vertices, where an edge connects two vertices, and a vertex is an interesting point. So a vertex can represent something on the problem, like a house or a gas company or water or a utility, as in the case of the utilities problem. And so when we talked about graphs, we also talked about the idea of planar graphs. So a planar graph is a graph that can be drawn only in the plane. And so when we say a graph can be drawn in the plane, we're saying that a graph has all edge crossings occur only at vertices. So we don't have any overlapping edges unless they occur at a vertex. Vertices. So the only way, if we have a graph where it looks like two things are crossing, it has to happen only at a vertex. We also talked about the idea of Euler's characteristic formula. And this is when we were talking about polyhedra, like cubes and such, where we had the vertices minus the faces minus the edges plus the vertices equals 2. And this is true for planar graphs. So this characteristic formula was true for planar graphs. And we use this when we were doing cubes and icosahedra, and basically when we're looking at our 5 regular polyhedra. So this was way back at the beginning of the semester, but we had this Euler characteristic formula where we counted all our vertices, we counted all our edges and our faces, we flattened them down onto the plane. We remembered we had that outside face and we counted it all up and it always added up to this. And so when we were looking at our graphs, we had 2 sort of special graphs that we cared about. We cared about K5, which was our complete graph on 5 vertices. And this looked like the star embedded in a pentagon. So we had the pentagon on the outside, and then we had the star embedded on the inside. Oops, I already used that edge. So we had that on the outside and the star embedded on the inside. So K5 is the first complete graph that's not planar. So it's the first non-planar complete graph. And we saw that when we played around with it, we tried to drag the edges and we couldn't figure out a way to make that planar. We also talked about bipartite graphs. And these were graphs that had 2 parts. And we talked very briefly about K33. And this is a complete bipartite graph. And so we had 3 vertices here. So there's 2 parts, each with 3 vertices, and we connected them across. Oops, my lines are a little bit wavy today. Too much caffeine. And so we said, we're going to leave this for later. And so we didn't talk much about, is this planar? Is this not? What's going on with this? And this is what we'll talk about today. And this is typically referenced as the utility problem. And so this is kind of where we're going to start today, is with the K33 graph. So with the utility problem, what you can think of is the utility problem says, I've got 3 houses, utility problem. So we've got 3 houses, and each needs to be connected to 3 different utilities. But the utilities can't cross. So if I've got my 3 houses and I'm trying to run power, water, and gas between these 3 houses, I can't let my lines cross for whatever reason. Maybe they all have to run at a certain height, but I can't let these lines cross. And so if we think of the, oops, let me drag this out of the way. We think about the utility problem as a bipartite graph. We have house 1, we have house 2, and we have house 3. And let's suppose we have water, and we have gas, and we have electricity. So very similar to the K33 setup. So the houses don't need to be connected to each other. And the utilities don't need to be connected to each other, but they needed to be connected across. So this is a perfect setup for a K33 for this bipartite graph. So we can start doing some setups where we can just start making our connections here. So we can do water connected, and we can, I'm going to do a little bit of sneak around here. We're going to do that, and then we're going to do that. So I've connected water to 1, 2, and 3 fine, and that's working out well for me. And I can connect my gas. I can connect, well, I can pull the gas around to house 1, gas to house 2, and gas to house 3. So water and gas are fine. But now when I go to do the electric, house 3 is fine. I can pull it all the way down around to house 1, still without connecting. But there's no way that I can get to house 2, because if I cross over directly from house 2, I intersect the green line between gas and house 3. So that's a problem here. If I had taken a different step and I had gone around the outside to house 2, I'm intersecting the line between water and house 3. So I have a problem here. So either way, there's no way that I can represent the utility problem or bipartite K33 on a planar graph. So this is proof by picture that K33, which is this graph, is not planar. So there's no way that we can represent, that we can solve this in the plane. So if we can't solve this in the plane, this is where mathematicians started to say, well, what can we do with this? And Euler's characteristic formula, we can still say, well, how many faces does this have? How many edges does this have? How many vertices does this have? We just now have the question where if we're connecting house 2 with electricity, how do we account for this extra face, this overlapping piece? And this is where we have to kind of expand our idea of what the plane looks like. And so this is where our mapping comes into play. And so in the resources, we talked a little bit about mapping on a torus. So let's take a look at that. So let me switch pages here. So I'm going to insert an image of the utility problem. Actually, let's leave that off for now. So let's see if I can do this where I can share the utility problem. Let's try this with the camera. Okay. So let's see if we're going to try this. Hopefully we can try this idea. So this is our torus. I'm not sure how well this is going to record, but we'll try this. So here is our utility problem. And so we've got our 3 houses, house 1, 2, and 3, and our utilities, water, sewer, and gas, or water, gas, and electric. And in this case, gas is the one that isn't connected yet. So water is connected to the houses in purple. Let me turn my light a little bit. So water is connected to the houses in purple. So we've got water connected here to house 1, over top to house 2, or sorry, to house 3, and then to house 2 here. And then we have house 1, it's connected around the top down to electric. And electric is connected to house 3 and house 2. And then in orange, we've got gas is connected to house 2, and then gas is connected to house over here to house 1. And so we need to connect gas to house 3. So if on the plane, if we just connected gas across to house here, we'd cross the yellow line. And so that's not going to work out for us. But if we tried to move gas around the top over here, we'd cross over the yellow line again. We connected through, oh, my stickies. Stick back down. My pipe cleaner is failing here. We tried to connect through here. We're crossing over the purple lines. So on a torus, what we have is we have the option is that we can now go through the hole in the center. So by allowing ourselves to go in multidimensional space, we can go through the torus and then end up connecting with house, what house am I trying to get to? House 3 through the top here. So now I'm not crossing any lines because I'm going through the hole in the center. So now my space works out well. This one should be connected there. And so I haven't crossed any of my pipe cleaners. So my utility lines are all set, and I've connected all of my utilities to my houses. So let's look at that on a diagram. So let me switch back to our screen. So in case you missed what that looked like, let's look at an image. So on our image, we have our houses. And here they put the utilities slightly out of order. So they changed the order of the utilities here between their water and their electric. But the idea here is that they took the line, and here is where they wrapped it around the back of the torus. They wrapped it through the torus and that through that center of that donut. And that's what really keeps it from crossing over anything else, is that it's behind all the other pieces. And so now we can do our edge counting. So we still have 6 vertices because we have 3 houses and 3 utilities. If we count our edges, we have the 3 edges from each utility. So notice that this edge here is a continuation of this edge. So that's just one edge there. Right, so we have to be careful how we're counting our edges. We have 3 edges from each utility, so 3 electric, 3 water, and 3 gas. So we have 9 total edges. And now when we're looking at our faces, if we look at our utility, if we look at back on our torus here, this is our torus, our 3-dimensional object makes it easy to count. We have the face that lives in between on the surface of the torus. So we have this face here. That's on the outside edge of the torus, on the donut. We have the face that lives next to it on the outside edge facing you. And then we have to figure out how many other faces we have. So we have a 3rd face that lives above the water. And then we continue that face around. So we're still above the water here. But that face also goes underneath the torus. So if we were looking, maybe this will show up on the screen. If we're looking at our torus, so think of our airplane pillow, your neck goes at the back of it, but the top of the airplane pillow also curves around to where your hair lays down. But then your hair lays down and it goes all the way around, right? So you could draw a circle around that, and that's still the same face. So that face still comes out, and it comes out and it's the same face on the other side of that purple curve here on the screen. You haven't changed the color of that face. So that's still blue all the way through here. And that's still blue all the way through the other side. So it's one face on the outside color. So you have a total of 3 faces. So Euler's formula says, well, we take our vertices minus our edges plus our faces. So 6 minus 9 plus 3, we get 0. So in this case, Euler's characteristic formula gives us 0. And it turns out that Euler's characteristic formula can give us kind of a categorization of different planar graphs, or different graphs, planar or non-planar. It's hard to imagine some of these graphs on 3-dimensional shapes and 2-dimensional spaces, but if we look at this representation on the left here, we've taken that torus and we've kind of smashed it down a little bit, and it makes it easier to count. So let's see how they built that left-hand graph. So let's build a 2D torus. And let's see how they built that. So if we take a torus, fancy way to do it, draw a circle, draw a smile, draw a little frown. There's my torus. And so if I think of this, and if I cut it with a little snip right through the center here, this turns it in. If I take my tube, there's my snip, there's one side of my snip, there's my other side of my snip. I've unwrapped my torus. So think about it as taking a donut and snipping it, and then you have your torus kind of like that, right? So here's your torus. So if I have my donut and I wrap it around and I snip it and then I unwrap it. And so now we take our snip and we take our scissors and we cut along the top edge. So along the top edge, then we have along our top edge and along our bottom edge. And we unwrap, so the sides have unwrapped. And then the inside is our torus. So oftentimes we keep our orientation the same, right? Because we're not twisting, we didn't flip one of our edges. We just wrapped it around. So we give our orientation. So we give our directions. So these are both upward. And we cut our scissors both this way. So now this is a representation of a torus. So if I were to glue this back together, I match the arrows back together. So when we're drawing a utility problem on one of these graphs, we can say, well, if I'm drawing a K4 on a graph, or let's do this on a new page. So let's draw a K4. So if we draw a K4 on a torus, we could say that we have our three-dimensional shape here, or we could say that we have our rectangle here. These are both the same representations. And so when we're looking at this, we can either draw our torus as our K4. Remember, a K4 looks like this in the plane. That's a K4 in the plane. So we could draw that same K4. We can say this looks like this. And just to make it interesting, we can draw it all the way around the circle here. And then let's draw it around and wrap it here. We're just going to wrap it around the torus, just to put it inside the loop to make it interesting. So this is our K4 on the plane. This is our K4 on a torus. But if we want to draw that K4 on a torus in a two-dimensional space, we take our K4. This is on the outside face of the torus. So we keep this here. And then we think about, well, how are we drawing this? If we think about how we snipped this, right, going back up to our diagram, we took our torus and we cut it in the edge up here. So that means we're cutting. So if I draw my little cut line, here's my cut line. So if I'm cutting this one line along here, that means that I have this line. Where's my right color? This line gets cut, and I'm going to give it a number, and it gets cut and it goes back to here. Because that's the line that's cut, one, and it curves back up to this guy. And so then when I take my cut line and then I cut it again with my scissors, when I did my second cut up here with my top, cutting along the top piece, which is opening up my donut, that means I have to cut over my top piece. So that means this one cuts here. And so that's my second matching line. So now when I'm counting my faces, I have my first face, and then my second face, I say, well, this is face 2, but this side of the face lives between 1 and 2. So this edge, this left edge, if I wrap it around, matches this little area here, matches with this little area here, because I've wrapped it around. So this is the same face. And since this face too, if I were to fold it back up, this is the same face. And the same way, this is the same face. So I have 4 vertices. And I have 1, 2, 3, 4, 5, 6 edges. and I have two faces. And so this means my Euler characteristic for the shape is equal to 0. So my torus has Euler characteristic 0 for this. And this is what we call, has to do with the idea of embeddings, which is what one of your videos talked about. So we aren't going to go too much more into this, but this is what they call the field of algebraic topology. We'll talk next week more about the idea of the Poincaré conjecture, which is where you can shrink a circle down to, or a sphere down to a point. And if you can take any object and shrink it down to a point, then it's the same object. And that's where we talk about topology. So the last couple of weeks of this course is really bringing the ideas of graph theory into algebraic topology, which is like what I took in grad school. So I'm taking you from a level where you're like, I can do this, to a level of like, which is like the whole point of this course is to see that you can do things that grad students can do, even if only just a little bit, but you can get there too. So that's what I've got for today. So do you have any questions on this?
No, that was definitely a better explanation of how the sides unfold and how they relate to each other, because in the video they didn't show how they unfolded it. So that definitely helped.
Okay. And you can do this with all sorts of strips, like Mobius strips, which are one-sided twists of paper. So it's a one-sided object with one edge. If you take a Mobius strip, like a piece of paper, and instead of just looping it around, if you give it a one twist and loop it around, then this is the diagram for that, or a Klein bottle, or things like that. I forget what these diagrams are actually called, but they're used a lot to describe multi-dimensional shapes in a way that you can't physically manipulate them.
Are we going to go into it next week with the two-cell embedding for the V minus E plus F equals 2 minus 2K? That was in one of the videos.
We'll talk briefly about the genus, which is what the 2K is, or the 2Chi.
Okay.
And that's where the Euler characteristic comes into play, is the genus part, and that helps characterize different shapes and different embeddings.
Okay.
But yeah, so this week is just getting you comfortable with the idea of algebraic topology, and then next week we'll take another step into it.
Okay. Well, that made me feel comfortable with it. Appreciate it.
Yeah, no problem. All right.
That's all I got. Thank you.
All right. Yeah, no problem. So I'll go ahead and stop recording. I can remember. So.